Hello. Oh, that's cool. Are you there?
Hello.
Yes, yes. How are you?
Fine. And how are you?
Fine, fine. So it is around 1 minute, and sir has joined or not?
I think he is joined.
Yes. Sir, are you ready? Everybody, sir?
Yes.
Yes. If possible, you can show a video for 2 or 3 minutes initially
Maybe.
before starting the lecture. Yeah, it is fine. So, good afternoon to everyone. In this session, today's speaker is Professor M.M. Tripathi sir, from BHU Varanasi, and he is going to talk on some Euler inequality for Fulcrunity curvature tensors and its applications. And to chair this session, I invite Dr. Poonam Gupta from Dr. Hari Singh Gaur, Central University, Sagar. He has been a PhD student of Professor Tripathi. So over to you, Dr. Poonam.
Thank you so much. Good afternoon to all, and I am very thankful to organizers Dr. Gauri Sankar and Dr. Krishnendu for giving me this opportunity. So for the afternoon session, we have a great mathematician who has had a distinguished work in the field of differential geometry. He has published more than 100 research papers in reputed international and national journals. He started his career from Lucknow University, and he served as assistant and associate professor there, and also had PhD from there. In 2007, he joined Banaras Hindu University as a professor, and most importantly, as Dr. Gauri Sankar told that, he was my PhD supervisor. He gave many invited talks all over the world and encourages students to do research in differential geometry. So now, without taking so much time, I request to our speaker, Professor Mukutmani Tripathi sir, to start the lecture.
Thank you so much, Professor Gauri Sankar ji, Professor Krishnendu Bhattacharya ji, and Dr. Poonam Gupta ji. I can take just maybe some couple of at least 1 minute, because there are just 47 people have joined so far, and the first slide is very important of this talk, at least to me. So I'm not a great mathematician, first of all. I still try to learn a lot of things, and how to express myself. Yes, giving a mathematical talk is a different thing, and talking something in general, it needs a lot of expertise in the language itself. But if you don't mind, I can say some things in Hindi language itself. I think everybody can understand. It is not much trouble. I started my PhD program under supervision of Professor Kamla Devi Singh. She is still very active, but not in mathematics. And I really feel, just without any reservation, gratefulness to her throughout my life. In fact, he changed the life. So if you have a good guide in any sense, your teacher, your mother, your father, or anyone who transforms your life into a betterment then it is really a wonderful thing. And so just motivated by her career and strictness and a lot of what to say, effective and efficient in every manner. So I started my PhD program under her supervision, and then I was quite lucky to get a position in Lucknow University itself. Served the Lucknow University for 17 years, and most of the time during these 17 years, I was put, or it was a compulsion, you can say, to study geometry rather than to teach geometry, and probably it was a blessing in disguise. So I had some good ideas to pursue there, and what was important that at stay in Lucknow University, I continued my seminar, and it was a one-to-one seminar. The audience was only Professor Kamala Devi Singh, and I was the speaker, and every day we met for 1 hour, almost 3-4 years, maybe more, after my PhD. So this was all about so learning mathematics is by doing seminars, and at the time of my PhD program, I think most of the results I could write on the board without any hesitation, and even along with their proofs. So that time there was no transparency and no such kind of things. So everything you had to write on the board. And you will be surprised that my PhD Viva Voce was continued more than 3 hours. Professor R.S. Misra was the PhD examiner, and I prepared some transparencies, and I was told to put all those things aside, come on the board with chalk and duster, and then he took my PhD thesis as well. So now you present yourself. So this was something I enjoyed, and it was my defense there. And then everything, as I used to say to my students, and hard work always pays, sometimes late, sometimes soon, but it hardly matters, and sometimes never. So it also happens. Then again, I had a chance to have some postdoctoral experience at Chonam National University in South Korea, and in the second visit, I was a visiting professor at Pohang Institute of Science and Technology. And in this manner, I continued my journey of research. The good point was to deliver a talk in Baltimore meeting of American Mathematical Society, and the idea was how one can live without tension in a best world. So how to say this phrase in the terms of differential geometry. And basically it was related with a lot of sharp inequalities relating with intrinsic and extrinsic invariants of a Riemannian submanifold sitting inside a Riemannian manifold. Anyhow, so I think we have now enough people here to start with. So with your permission, and okay, one thing I'm missing, I must not forget. Anyhow, this talk, today's talk is dedicated to one of the great geometers of the world, Professor R.S. Fulcrunity, sir. We all feel blessed and energetic just by taking his name. And if I think that what a Riemannian geometry student should start with, then I think one must go through the paper of Gauss, and then at the second place, I have seen that the paper has been shared in the group by Professor Gauri Shankar, the paper by Riemann himself, which was published in Nature, and then to my mind, the paper by Professor Fulcrunity. the crux of curvature and metric published in Annals of Mathematics. So probably, not probably, in fact, it was his PhD program, and it was really one of the seminal work in the area of Riemann geometry. Once you have these three papers in your mind, then you can start learning Riemann geometry. So I think I can start now. So may I start sharing my slides? Yes, please.
Yes,
Can I
yes, yes.
Okay. Okay. So here is a window, and here is my file. Just a moment. Here is the synthesis, and here is the file. Okay. Okay.
Hello.
Is it visible? Is it
Yes.
visible?
Yes,
Yes, it is.
Okay, so it is something about Vintigian inequality for Fulcrunity tensors and its applications.
Sir, increase the size, make
Now
it.
come to yes, please.
Increase
Yes.
the size.
Okay.
It is just 64.3%.
It is
Just
okay?
increase from there.
I mean,
Yes, sir.
a little
It is fine
bit.
now. It is fine.
It's fine.
Yeah.
Okay. I think it is also fine because I can see the whole slide on the screen, or maybe a little bit more. So this is okay. Okay.
Yes, it is.
Okay. So come to the next slide. Yes. This is the tribute to God, and we believe that the manifold, in fact, started from there. Even in his original lecture, Riemann himself said manifoldness rather than manifold. So I'm listening some more noise from other speakers. Please mute yourself. So the idea of manifoldness, if I say in our language, this is the concept of Vishwarupam, what Lord Krishna showed to Arjuna. And this stone you can see, this is in the tallest temple of Lord Shiva on the earth, situated inside the campus of Banaras Hindu University. And first time I saw it in 1990 when I visited this campus for a conference. And here is a verse from Shvetaropanishad. I think I must read it the way it must be read. Adis sanyog nimitta hetu parastrikala kalopi drishtah tam vishwarupam bhavabhutamidyam devam स्वचित्तस्थमुपास्य पूर्वम. वह मूल कारण, संयोग का निमित्त कारण, तीनों कालों से परे, कला रहित भी जाना जाता है, उस विश्वरूप उत्पत्ति स्थान स्तुति के योग्य उस पुरातन देव की जो सबके चित्तस्थ है, हम उपासना करें. The beginning, he, the efficient cause of combinations, as beyond the three times, maybe of any dimension, without parts also may be connected or disconnected. Is he to be seen as the manifold, the source of being, worthy of praise, God in one's self?
Please unmute, sir. You have been muted.
Okay. I'm sorry. I think I have to start again. So you can see this slide. This is a stone in the tallest temple of Lord Shiva, situated in Banaras Hindu University. And I visited this temple in 1990 first time. So this is one of the attributes to God in the name of manifold. Even in his lecture, the Riemann himself said manifoldness rather than manifold. And if we say it in Hindi language, so it is the idea of or the concept of Vishwarupam. The Swarup Lord Krishna showed to Arjuna in his lectures of Bhagavad Gita. And I must read the way it should be. So it is a verse from Sweta Sataropanishad. Adis संयोग निमित्त हेतु परस्त्रिकालाद कलोपि दृष्टः तं विश्वरूपं भवभूतमीड्यं देवं स्वचित्तस्थमुपास्य पूर्वं. The beginning he, the efficient cause of combinations, as beyond the three times without parts also, is he to be seen as the manifold, the source of being, worthy of praise, God in oneself, abiding worship, the Brahman. So this is the thing. So with this small religious thought, I can proceed to the talk of the today. And here is the table of contents. So we will be having a brief review, then some early examples, and then about Fulcrunity tensor, and then the idea of integer inequality, and then how to apply it in the theory of Riemann in submanifolds, and then further developments in this area in different sub-areas, you can say, in the case of pseudo-Riemannian geometry, in Hermitian geometry, in Sasakian geometry, in quaternionic geometry, and then in the submersion theory, and also in the Mobius geometry, statistical submanifold theory, and then the word product submanifolds. And recently we have the idea of normal Ricci curvature. So this inequality is still in the process. This is the last development in this area. And here we start with a brief review. I think it is quite visible for us. So this is according to Chern, S.S. Chern, the problem of discovering simple, sharp relationships between intrinsic and extrinsic invariants of Riemann in submanifolds. And according to Chern, this is one of the most fundamental problems in submanifold theory. In fact, he said this kind of, he gave this kind of a statement when the
You are not audible, sir. You are not audible, sir.
I think he has some net connectivity issue, so please wait for him.
Hello.
Can you please hear me?
Yes.
हाँ सर, हाँ सर.
I'm sorry for the bad internet. Oof.
Okay, no problem.
So the first slide was completed or not? This
Oh, sir.
one.
No.
Okay, so in the classical surface theory, we know that a surface.
Sir, please start from beginning.
Yes, it is the start of the beginning.
Okay, sir.
Okay, sir.
Okay, maybe a little bit more. So in classical surface theory, for every surface, regular surface in Euclidean 3 space, we have Euler inequality, which says that the Gaussian curvature is bounded above by the squared mean curvature. And this inequality, in fact, follows from the fact that the Gaussian curvature is the product of Eulerian principal curvatures, and the mean curvature is the average of the two. And the equality case in this inequality is true at every point of the surface if and only if the surface is totally umbilical. It simply means that the two principal curvatures, they are identical. And there is a result of Meusner which says that the surface is totally umbilical if and only if either it is a part of a plane or it is a part of a round sphere. So with this inequality, I think it was the motivation point for the Peter Vintigen, and he lived a very short life like Riemann. He was one of the nice German mathematician, but unfortunately he lost his life very soon, and before his death in 1979 he in fact established this inequality, and this inequality is for a surface in Euclidean 4 space rather than in Euclidean 3 space. So sometimes some surfaces you cannot even accommodate in Euclidean 3 space, and you need to put them in Euclidean 4 space. So this platform is richer than the class of surfaces inside Euclidean 3 space. And here he proved that the Gaussian curvature is bounded above by the squared mean curvature minus absolute value of the normal curvature. And this normal curvature with respect to an orthonormal frame where E1, E2 are tangent to the surface and E3 perp and E4 perp are orthogonal to the surface, and this normal curvature is defined by this, where this Langle wrangle, it is simply the Euclidean inner product at every point of the surface. Okay. This inequality was called Vintigen inequality by D. Smith et al. In 1999. So here you can see the picture of Vintigen, Peter Vintigen. It is him. Here he is in a conference. Here he is in a conference, and here is Professor Solanke, and he is his PhD supervisor. And now suppose that M2 is a surface in a 2 plus m dimensional Riemannian manifold. So here the codimension is greater than or equal to 2, it is assumed. And then the ellipse of the curvature at a point P of the surface is in fact defined to be the image of the unit circle in the tangent plane under the map second fundamental form in the normal plane. So in this manner, this capital epsilon, and it is given by this expression sigma xx, where x is a unit vector in the tangent plane of the surface and sigma is the second fundamental form of the immersion. And with this description, in 1983, the inequality of in fact, in this inequality 3.3 in this paper, they obtained an extension of the Vintigen inequality for regular surfaces in a real space form. So a real space form is a Riemannian manifold of constant sectional curvature, and the model spaces are the Euclidean spaces and the spheres and the hyperbolic spaces. And in this case, if the constant sectional curvature is C, then the Gaussian curvature is bounded above by this expression, where this is the squared mean curvature and this is the absolute value of the normal curvature and this is the constant sectional curvature. And the equality case of 1.3 is true, and therefore also in the previous inequality of the Vintigen, if and only if the ellipse of curvature is a circle. So with this description, okay, of course, we will discuss this point of view again, but as a relaxation, without assuming much, a similar result was proved by Bang-Yan Chen in 1996. It is a paper in Glasgow Math Journal. Here he proved that suppose that M is an n-dimensional Riemannian submanifold of a real space form of any dimension. So here he did not put any restriction on the codimension. And in this case, he obtained this inequality, where this tau nor is the normalized scalar curvature, and this is the squared mean curvature of the Riemannian submanifold, and C is the constant sectional curvature of the ambient manifold. And here this tau nor is in fact denoted by this expression. This, and in fact this. Yes, this normalized factor in fact gives us some sort of edginess in calculations, and sometimes this, instead of scalar curvature, we use the normalized scalar curvature. The scalar curvature in fact defined by Chen is slightly different from the usual scalar curvature what we learn from the books. So it is in fact half of the scalar curvature usually what we get in the books. But why Chen prefers this tau? Because this becomes exactly the Gaussian curvature in the dimension 2. So that's why he takes half of the scalar curvature to be scalar curvature, and this normalized factor is put to get certain things in order. So this is called the normalized scalar curvature. And here this inequality is in fact proved for ambient manifold to be a real space form. Suppose we are just given a Riemannian manifold and we are not having any idea about constant sectional curvature. Then what to do? So for that we have a result proved in 2005. This result I proved while I was visiting on a short visit to Yamagata University in 2005. And here we have given this result. Just I have taken an n-dimensional Riemannian submanifold of an m-dimensional Riemannian manifold. And there is no restriction on the sectional curvature, and there is no restriction on the codimension. And then we obtained this inequality. Here the normalized scalar curvature of the Riemannian submanifold is bounded above by the squared mean curvature plus normalized scalar curvature of the tangent spaces in the ambient manifold. So this is something, I mean, this phrase we will explain in detail when I will explain you the idea of Riemannian submanifolds. So, and here, now from this inequality, if I take m tilde to be real space form, then in that case, this normalized scalar curvature of TPM in the ambient manifold m tilde, it exactly becomes the constant sectional curvature C. Okay, here you can see, here is Professor Koji Matsumoto. He visited Banaras Hindu University few years back, and on the right side he is Professor Ulrich Kowalski. He also has been a good friend of Professor Fulcrunity. He is one of the great geometer from Czech Republic, and few months ago he passed away. I had a chance to visit Professor Kowalski once in the Charles University in Prague. Now come to this development. So in 1999, Smet and Billen and Westline and Rankin, they proposed the following conjecture. And this conjecture says that suppose that Mn is a Riemannian submanifold of a real space form of constant sectional curvature C with n greater than or equal to 2. It means it has to be I'm sorry. It is it's okay. And then in this case, the normalized scalar curvature Riemannian manifold is bounded above by the squared mean curvature minus normalized normal scalar curvature and plus the constant sectional curvature C. And where this normalized normal scalar curvature, this is given by this expression. This conjecture 1.3, it is known to be DDB conjecture. DDBB conjecture, because here you can see D, D and B and B. Or sometimes it is known to be normal scalar curvature conjecture. Or sometimes it is known to be conjecture on Wintgen inequality. So all these phrases are in use. This inequality 1.6, this is also known as DDBB inequality or Wintgen inequality or generalized Wintgen inequality. But usually we prefer to call it Wintgen inequality. And submanifolds satisfying the equality case of the Wintgen inequality, they are known as to be Wintgen ideal submanifolds. And in case of trivial normal connection, the Wintgen inequality just reduces to chains inequality. Okay, so in this paper, DDBB proved their conjecture in affirmative for submanifolds of arbitrary dimension and codimension 2 in real space forms of constant sectional curvature C, and presented a detailed characterization of the equality case of the Wintgen inequality in terms of the shape operators of the Riemannian submanifold in the real space form m tilde of dimension n plus 2 and of constant sectional curvature C. In fact, they proved the following result. So this result says that if Mn is a Riemannian submanifold of a real space form of constant sectional curvature C, and then at every point this Wintgen inequality is satisfied. Here, in fact, the codimension is restricted to 2, with the equality case holding if and only if there is an orthonormal basis of the tangent space and an orthonormal basis of the normal space at every point to the submanifold, such that the shape operators can be written in the matrix form represented by these two expressions. So here you can see A, B, B, and here it is B minus B, and all other entries are 0, and here the diagonals are all A. Now come to 2007. In this year, Dylan and his collaborators, they translated the DDB. So this is a good breakthrough in proof of DDB conjecture in general. So they translated the DDBB conjecture equivalent to an algebraic inequality. So the original DDBB conjecture is true if and only if every set A1, A2, AM of traceless symmetric n cross n matrices satisfies this algebraic inequality. This is given by the difference of their products like this. So the whole geometric problem now has been converted into an algebraic problem. And for fixed n and m greater than or equal to 2, this inequality is in fact known as PNM conjecture, according to Choi and Liu. This was the definition given by them. So now their emphasis is to prove this inequality, and now the whole problem is of algebra rather than of geometry. Then in 2008, yes.
Sir, how we are getting these AI's metric? Are these shape operator?
Shape operators are always represented by matrices.
Okay, so that's why we are writing. Okay, sir.
Otherwise, how? In fact, when you go for obtaining the Eulerian normal curvature, so what are you doing? You are obtaining the eigenvectors and eigenvalues of the shape operators of a surface in Euclidean 3 space. It's okay?
Right, sir.
So now we see that the DDBB conjecture is converted to a conjecture which is PNM conjecture, and this is about matrices. So the whole problem has been shifted from geometry to algebra. Okay. And then in 2008, Choi and Liu, they observed that this DDBB conjecture was true if and only if this inequality is true, where these A's are real numbers. So it is a complete algebraic transformation of the PNM conjecture. And in fact, what is happening, I have seen hundreds of papers on DDBB inequality or Bintijan inequality in different situations, and most of the time they are using this equation 1.8 to be crucial in their calculations. So in 2008, Choi and Liu, they proved that the DDBB conjecture was true for all three-dimensional submanifolds of arbitrary codimension. Moreover, they gave a characterization for the equality case. In fact, they proved the following theorem. And the theorem is here is a picture of Liu, what I have obtained from his website. So they proved that suppose that M3 is a three-dimensional Riemannian submanifold of a real space form with codimension M greater than or equal to 2, then this Bintijan inequality is true And the equality case is satisfied identically if and only if with respect to a suitable orthonormal frame, E1, E2, E3 on M, and an orthonormal frame E3 plus 1 per to E3 plus M per of the normal bundle of the submanifold. The matrices of the shape operators. So these are the shape operators with respect to every orthogonal vector to the submanifold. R is running from 3 plus 1 to 3 plus M. They take this form. So the first shape operator is of this kind, the second shape operator is of this kind, and the third one is of just a scalar or a diagonal matrix, and the remaining are just zero. Finally, in 2008, in the same year, Gay and Tong, they proved DDVB conjecture for every submanifold, and in 2007, in fact, the paper was published in 2011, but it was in 2007 and 8. Lu, he proved he proved the DDVB conjecture in affirmative independently in a different manner, and he also discussed equality cases. And what was the settlement now? The settlement is like this. In fact, in 2008, Gay and Tong, they proved the equivalent PNM conjecture as following. Like this. So every set of real symmetric n cross n matrices, it satisfies this inequality. This norm is in fact coming from the, Hilbert-Smith norm. So it is the same thing. Where the equality holds if and only if under some rotation all ARs are zero except two matrices which can be written as PH1 PT. PT is for the transpose and PH2 PT. So where this P is an n cross n orthogonal matrix, and H1 and H2, they take this form. Here you can see. So he is Tong and he is Lu, young Chinese prodigy. Now let me discuss some examples before proceeding further. So here is so these are the examples before 1999. So totally umbilical submanifolds of real space forms, they are trivially Windigian ideal. And for a classification, there is a long paper by Bang-Yan Chen in 1973. In fact, in 1973, he came up with his first book on geometry of submanifolds at a very young age. And in the same year, he published this nice paper. And then one more example, BC from the first paper on DDVB conjecture. So here is a surface in real space form of dimension 4. And the ellipse of the curvature is a circle, and then they proved that this is a Windigian ideal. In fact, we have remarked this earlier also. And then in this example, a minimal surface R4 is called superminimal if the ellipse of curvature is a circle. So a cylinder on a superminimal surface in R4, this is again Windigian ideal. Examples of superminimal surfaces in R4, they are in fact holomorphic curves in two-dimensional complex Euclidean space. Here the dimension is the complex dimension. And the complex cylinders on holomorphic planar curves, they are in fact Windigian ideal. More generally, any complex hypersurface of n plus 1 dimensional complex Euclidean space with the rank of the shape operator at most 2, they all are Vintagian ideal. Any such complete hypersurface must be a complex cylinder. Here is a result in 1972. In this example, one sees that any word product decomposition of a real space form by this decomposition, here f is the warping function, and then taking a super minimal surface in the real space form of constant sectional curvature C prime, the submanifold this of this, in fact, it becomes Vintagian ideal. Here is one more nice example. Suppose that J is a complex structure on three-dimensional complex Euclidean space. This complex structure means, in fact, it is one of the model examples of complex manifolds with constant holomorphic sectional curvature 0. And here suppose that phi is the projection of the complex structure J of C3 onto the tangent bundle of 5-dimensional sphere inside the 3-dimensional complex Euclidean space. Here the dimension is 3, means complex dimension, so its real dimension is 6. And such that this J is J operated on n, where n is the outer normal of the sphere, then this J in fact induces a Sasakian structure on this odd-dimensional sphere. And this nice result one can obtain in the book of first book on contact geometry by David Blair in 1976. I feel honored and sometimes happy to have interaction with David Blair once in Baltimore meeting in 2002 in US, and once in an international conference at Zonguldak city in Turkey. And then we interacted on some ideas of concircular contact geometry and wrote a paper together. And probably that was the first paper in contact concircular geometry published in Journal of Korean Mathematical Society in 2005. So here suppose that pi is the half vibration of 5-dimensional sphere to 2-dimensional complex projective space, and here is some holomorphic sectional curvature is taken to be 4 instead of 2. Yesterday you have seen that how Professor Seshadri took the holomorphic sectional curvature to be 2 for some normalizing process. And then suppose phi is a map from M1 to Cp to 4. This is in fact a holomorphic curve, and PM1 be the circle bundle over M1 induced by the half vibration, and then psi is the emergence such that this diagram is commutative. Then this psi is in fact invariant immersion in the sense of Yano and Ishihara. It simply means that the differential of the map psi is phi invariant, and then this invariant immersion in the Sasakian space form S51 with the structure vector field J to be tangent along this this map psi. This is the holomorphic curve. And then this sigma psi is the second fundamental form of psi, and sigma phi is the second fundamental form of phi. Then the basic formulas for such submanifolds, they imply that these expressions are true. And then ultimately this emergent psi, this becomes minimal and Vintagian ideal. And but in these examples, in fact, they are either totally umbilical or and thus they have zero normal curvature or minimal. So if there are any non-minimal examples and later on people obtained non-minimal vintage ideal sum as well. Here I can give some more idea about. Here is one more example. It is one of the recent examples given by Ion Mihai in 2016, and in fact, Ion Mihai is my first foreign collaborator, and we wrote a long paper in 2000 on some sort of some manifolds of framed metric manifolds. These framed metric manifolds are a kind of generalizations of complex and Sasaki geometry together. So here is one nice example. So a Whitney 2 sphere first is defined. It is as an immersion of the unit sphere S2 in R3 with center at the origin, and this unit sphere is immersed into R4, and the immersion is given by this expression. Here R is a positive number and C is a fixed vector in R4, and then this number R and the vector C, they are called the radius and center of the Whitney 2 sphere. And this Whitney 2 sphere is in fact Vintage ideal. Here's one more example given by Mihai and Roxell in 1981 and Mihai in 2016. The rotation surfaces of Ranseno. So it is defined by the immersion of this R cross 0 to 2 pi into R4, and the immersion is given by this expression U and V. So here are U cos B, cos U sin B, sin U cos B, sin U sin B. R is a positive C infinity function, and its ellipse of curvature is circle if and only if either this expression is true or this expression is true. In the first case, the rotation surface is the tensor product of an equilateral hyperbola and a unit circle, and in the second case, it becomes tensor product of a lemniscate of Bernoulli and a unit circle. So this is one classical example, and in these two cases, the Ranseno's rotation surface, it becomes vintage and ideal. Here is some idea about superminimal surfaces. In fact, a superminimal surface is defined to be a surface in a Riemannian manifold of dimension 4 if the ellipse of curvature is a circle. This definition was given in 1984 by Friedrich. So, and a superminimal surface, this is in fact always a minimal surface. And here is one example, like this, the graph of holomorphic functions, like this. U is an open subset of the complex plane and F is any holomorphic function. So this graph is in fact a superminimal surface. In 1984, Friedrich proved that superminimal surfaces are characterized by the property that the lift into the twistor space is holomorphic and horizontal. In case of the ambient 4 manifold being a space of constant sectional curvature, I mean real space form, long back in 1928, it was proved that the family of superminimal immersions depends on two holomorphic functions. In 1984, Robert Bryant, he proved that every compact Riemann surface admits a conformal superminimal immersion into ordinary 4 sphere. Who is Robert Bryant? He was president of American Mathematical Society, and he visited Banaras Hindu University in 2016. And we must feel gratitude to Professor R.S. Fulcrunity, who was instrumental in getting this nice conference with the cooperation of American Mathematical Society at Banaras Hindu University in 2016. So here you can see Robert Bryant giving a talk in the main hall of the university, Banaras Hindu University. You can see him sitting beside Professor R.S. Kulkarni in the inaugural function of that conference. I was lucky to be snapped besides him in that conference and spent some time with him together at one evening on the banks of river Ganges. So here you can see Robert Bryant is in the mid here, and here is Professor Gauri Shankar. Here is Professor Venkatesh. Yesterday you have his talk. So for an oriented plane E in R4, suppose E perp is the orthogonal complement with the orientation given by the condition this. Then two oriented planes are called oriented isoclinic if either E is F perp or the projection is non-trivial. Non-trivial conformal map preserving the orientations. So consider an oriented surface in four-dimensional Riemannian manifold, and if gamma is a curve in the ambient manifold, then denote by tau gamma the parallel displacement along gamma in the tangent bundle, and then the surface M2 is called a negatively oriented isoclinic surface if for every curve gamma in M2 from X to Y, the planes this and this are negatively oriented isoclinic planes in this. And then it was proved by Friedrich and also long back in 1902 that an immersion is superminimal if and only if it is negatively oriented isoclinic. Moreover, recently in 2009, the authors established a representation formula for superminimal surfaces in R4 in terms of these pairs H1 and H2. Okay. Obviously, these Bintigen ideal surfaces in R4, they are exactly superminimal surfaces. Now come to the main thought of today. Because I was watching that proving Bintigen-like inequalities or Bintigen inequalities in different situations, the people were following the same long method of doing calculations and then coming to similar kind of conclusions. So here it was necessary to give a general theory so that I could obtain those inequalities just by applying the theory within a couple of lines or very short proofs. So the idea was to consider an algebraic Gauss equation related with a Riemannian manifold along with some Riemann vector bundle attached to that Riemannian manifold. And this kind of treatment I did successfully in several other cases in 2011, and it was for chain-Ricci inequalities, and in 2017 it was for Casarotti inequalities. Felix Casarotti is also famous for his Casarotti curvature. Because of the big development of Gauss, the Casarotti curvature could not get much attention in the mathematical world. But before his death in 1889 and 1890, Felix Casarotti wrote a couple of papers giving his ideas on that kind of curvature, what today is known as Casarotti curvature. And this curvature has many good applications in mechanical engineering problems as well. But that is a different idea, and that is not the talk of today. So here I now start with the Fulcrunity tensors. Suppose that T is an algebraic curvature tensor in a real vector space V. Here I write CF because in his original exposition, Kulkarni sir considered a inner product space rather than a real vector space. So here I am not considering any inner product, I am just working in a real vector space. So this is in fact a 0-4 tensor, and it satisfies these three R. You can see your hero, Professor R.S. Kulkarni, one more figure, delivering a lecture. One more nice picture is here. It was his seminal paper, appeared in Annals of Mathematics in 1970, probably. I think 1970. Maybe tomorrow you will get several good ideas about curvature and metric by himself only. So here this algebraic curvature tensor T is a 0-4 tensor. It means it is a covariant tensor of order 4 on a real vector space. I don't consider any inner product on the vector space, and it satisfies these symmetry or skew symmetry conditions. So here you can see that T is skew symmetric in first two slots, and then it is skew symmetric in last two slots, and then it satisfies an algebraic Bianchi identity. You can see that here I have written XYZ in the cyclic order, XYZ, then YZX, and then ZXY. So if T satisfies these three conditions, then it is called an algebraic curvature tensor. And in fact, one can check that if these three conditions are satisfied, then these two conditions are also satisfied. In fact, to be more precise, I have proved that if I take any two of these three conditions and any one of these two conditions, then the remaining two conditions are satisfied. And this treatment now I'm just propagating in my master's classes, and every year I used to prove these good results in the classrooms. So next, suppose that Mg is an n-dimensional Riemannian manifold. G is the Riemannian metric on M, and this time we take a field T of algebraic curvature tensors. Then I call it Kulkarni curvature on M, although it is known as curvature-like tensor or generalized curvature tensor. But because of his seminal work on this kind of structures, in fact, Kulkarni gave curvature structures, and that was more rich than this Kulkarni tensor. But here for our purpose, I am just concentrating on this Kulkarni tensor only. And with this definition, suppose that T is a Kulkarni tensor on a Riemannian manifold M. Now suppose that pi k is a k-plane section of the tangent space TPM, and E1 to Ek, it is an orthonormal basis of pi k. Then we denote this KTIJ as T operating on EI, EJ, EJ, EI. This EI, EJ, they are running through E1, E2, Ek. With this description, this TK scalar curvature of the K-plane section, it is defined by this expression. All these definitions I have given in my paper in 2011. Then I can normalize this K scalar curvature, and this is called normalized TK scalar curvature of the K-plane section, and it is defined by this equation 3.8. For a plane section pi 2, here the dimension is 2, so it is just a plane section. The T2 scalar curvature is exactly T sectional curvature of pi 2. So here is the treatment of this T-sectional curvature given in a paper by Chen et al. In 2005, and this was one of the motivation point for me. And also in a paper by John Bolton and his collaborators in 2009. So suppose U1 to En is an orthonormal basis for the tangent space TPM at a point P. Then this Tn scalar curvature tau TPM is exactly T scalar curvature of M at P. And this definition was given in this paper of Bolton. And then one can normalize this scalar curvature. This is the T normalized scalar curvature at P, and it is defined to be so just it is multiplied by one quantity 2 upon n minus 1. So of course one has to take the dimension n to be greater than 1. So T chain invariant is also defined in this manner. Delta T, it is tau Tp minus infimum of the sectional curvatures of pi 2 with respect to Fulcrunity tensor T. For a plane section pi 2, we note that all these three expressions, they are identical. If T is replaced by the Riemann, so what are the examples of a Fulcrunity curvature tensor? So, for example, one simple example is an expression GYZ into GXW minus GXZ into GYW. This is one GYW. This expression is so this also it means that T operated on XYZ is defined by this expression. So this is a Fulcrunity curvature tensor. The Riemann curvature tensor itself is a Fulcrunity tensor. The conformal curvature tensor is one non-trivial example of Fulcrunity curvature tensor. But not all curvature tensors written in the literature, they are Fulcrunity tensors. For example, a projective curvature tensor, it is not a Fulcrunity tensor. Even it does not satisfy the symmetric properties of a Riemann curvature tensor. Anyhow, so if T is replaced by the Riemann curvature tensor, then T sectional curvature KT, T scalar curvature tau T, normalized T scalar curvature tau T nor, T K scalar curvature tau T pi K, normalized T K scalar curvature tau T nor pi K, and T chain invariant delta T, they reduce to the ordinary sectional curvature, the scalar curvature, the normalized scalar curvature, K scalar curvature, normalized K scalar curvature, and chain invariant respectively. So with this description, now I want to give a simple proof of Wintgen inequality for Fulcrunity tensors. Suppose MG is an n-dimensional Riemannian manifold, and suppose BGB be an m-dimensional Riemann vector bundle over M, and suppose zeta is a b-valued symmetric 1-2 tensor field, and T a 0-4 tensor field T on M satisfying this equation. Then this equation 4.1, it is called an algebraic Gauss equation. And in this case, if T satisfies an algebraic Gauss equation, it must be a Fulcrunity tensor. There is no other way. In fact, it satisfies all the properties of a Fulcrunity tensor. Now suppose E1 to En be an orthonormal basis of the tangent space, and ER perp belong to an orthonormal basis of the Riemann vector bundle over M at P, and then we put zeta Rij by this expression and trace of zeta by this simple expression. Then squared norm of zeta is given by this expression, and squared norm of trace zeta is given by this expression. Okay. And then I needed a definition, and to formulate this definition, it took me several months, in fact. So I defined Vintigian scalar curvature and normalized Vintigian scalar curvature associated with zeta by these two expressions. Okay. And then I will take the account of this definition in my result, and my result is this, theorem 4.2. In fact, you could have been see this result in the abstract of the talk. So suppose that Mg is an n-dimensional Riemann manifold with n greater than or equal to 2. And suppose BGB is an m-dimensional Riemann vector bundle over M with m greater than or equal to 2. And suppose zeta is a b-valued symmetric 1-2 tensor field and T a Fulcrunity curvature tensor on M satisfying the algebraic Gauss equation. Then the normalized T scalar curvature and normalized Vintigian scalar curvature associated with zeta, they satisfy this simple inequality. Okay. If M is 2, so I can call this as Vintigian inequality for Fulcrunity curvature tensor. If M is 2, the equality case of 4.4 is satisfied identically if and only if, with respect to a suitable orthonormal frame E1, E2, En on M, and an orthonormal frame En plus 1, here I think it should be, just a moment, let me make a correction. Okay, so here yes, here it is the case M is 2. Therefore, I have only two members in orthonormal frame of the Riemann vector bundle BGB. And then the matrix is, yes.
Sir,
yes.
In this equation, it is N or M?
Where?
In equation 4.4.
Yes.
It is N or M?
It is N. It is the dimension. It is the dimension of the manifold.
Okay.
Here you can see this trace. This trace is just I is 1 to n zeta ei. Okay.
Okay.
It is okay. So here I have taken the two cases. So if M is 2, then the equality is satisfied if we have some suitable orthonormal frame this on M and an orthonormal frame this on BGB. Says that the matrices zeta Rij, they take the forms this and this, where A and B are local real functions on M. If M is greater than 2, then the equality case is satisfied identically if and only with respect to a suitable orthonormal frame E1, E2, En on M, and an orthonormal frame En plus 1 to En plus M of the Riemann vector bundle. The matrices take this form. Here it is A1 plus B, here it is A1 minus B, and A1 to A1. Here it is A2, 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 A2. So all the diagonals are A2, and here it is B, B. and then zeta n plus 3 ij, it is just A3 times identity matrix, and all other matrices, they comes to be 0. And here I am giving the proof. This proof is simple. So from the algebraic Gauss equation, I write KTIJ, and this comes out to be this expression. Then from here I obtain the scalar curvature with respect to Fulcrunity tensor T, and I come with this equation. Then we calculate squared norm of the trace zeta, and I come with this expression. And then I use 4.3 in this inequality. So this 4.3 in this inequality we use, and then we get simply this expression. And from the previous two equations, we obtain this expression. Of course, one has to work out, but here I have just written what I obtained. And then from these two equations, we obtain our inequality. Okay. And for the case m equal to 2, the characterization of the equality case is similar to the proof of theorem 4.1 in this paper. And the remaining part, it is concerned with the equality case, and it is similar to a corollary in the paper of Gay and Tong in 2008. So this inequality, in fact, this inequality, this can be applied in many situations. So you are having different kinds of submanifolds in real space forms, in complex space forms, in Sasakian space forms, in quaternionic space forms, many other places. So wherever you have this kind of situation like algebraic Gauss equation, you can apply this simple result, and you can obtain your result very quickly. So, for example, I can obtain a general kind of Vintigian inequality for any Riemannian submanifold by applying that theory. So suppose that Mg is an n-dimensional Riemannian manifold. Everybody knows about Riemann-Christoffel curvature tensor, which is of type 04, given by this expression. And then this Kij is denoted by R, EI, EJ, EJ, EI, E1, E2, EK. This is an orthonormal basis of a K-plane section. And from here, a K scalar curvature can be written by this expression 5.2. And then normalized K scalar curvature, it is given by this equation 5.3. In fact, this tau pi k is multiplied by 2 over k into k minus 1. And then the scalar curvature of the submanifold M at any point P is given by this expression 5.4, and one can normalize the scalar curvature, and it is given by this equation 5.5. So this tau is in fact multiplied by 2 over n into n minus 1. And for a plane section pi 2, in fact, 2 scalar curvature is exactly the sectional curvature of the plane section. In fact, for a two-dimensional Riemannian manifold, the scalar curvature becomes its Gaussian curvature. Classically, the scalar curvature is defined by 2 tau, but here we are following the definition of Bangian chain, so we are just taking tau. The chain invariant is defined by chain in 1993 first time, and this was the first modern intrinsic invariant apart from classical curvature invariants like Ricci curvature and scalar curvature. And now suppose Mg is an n-dimensional Riemannian submanifold of an n plus m dimensional Riemannian manifold m tilde g tilde. Then these are the Gauss and Bingarten formulas. I think we already know all these things in this workshop. And here is the nice relation between second fundamental form and the shape operator. Because of this relation, you are able to write down its matrix representation always. This is the classical equation of Gauss for a Riemannian submanifold. In a Riemannian manifold, this R tilde is the Riemann-Christoffel curvature of the Riemannian ambient manifold. R is the induced Riemann-Christoffel curvature tensor on the Riemannian submanifold. This is the Ricci equation for this R perp. This is the normal curvature, you can say, normal curvature tensor. So this is defined by this expression. In fact, this normal curvature operator is defined by this expression, where this del perp is the derivative induced in the normal bundle of the submanifold. And suppose E1, E2, En be an orthonormal frame for M, and ER perp belongs to an orthonormal frame for the normal bundle of the submanifold. Then this G tilde and sigma EI, EJ and ER perp, it is denoted by this real number sigma R IJ. And here this is the commutator of these two matrices in one sense, and this comes out to be this expression. And this is the squared norm of the second fundamental form, and it is calculated by this expression. The mean curvature vector of the Riemannian submanifold is the average of the trace of second fundamental form, and it is given by this expression. The normal scalar curvature of M at P is defined by this expression in 2007 by Dillon and his collaborators. And the normalized normal scalar curvature of M at P, it is defined by this expression. The definition of normalized normal scalar curvature given by equation 5.9, in fact, it corresponds to the definition of normal scalar curvature given by D. Smith and his collaborators in 1999. Second fundamental form of the immersion by mu sigma, and normalized Vintigian scalar curvature associated with sigma by mu sigma norm, and so that we have these two expressions. This normalized Vintigian scalar curvature, it is called as normalized scalar normal curvature also by Ion Mihai in 2014 paper. And if R tilde xy n1 n2 is 0, then one can calculate that this R perp EI, EJ, ER perp, ES perp is given by this expression. And consequently, this mu sigma becomes normal scalar curvature, and mu sigma naught becomes normalized normal scalar curvature. So our definition, what I gave in the setting of Fulcrunity tensor satisfying algebraic Gauss equation, now that becomes very much suitable for our purpose when we go for applying the theory into case of Riemannian submanifolds. And then from this equation of Gauss, we can obtain these to this equation. So this equation is just this is just the scalar curvature of the Riemannian submanifold, and this is the scalar curvature of the Riemannian submanifold with respect to ambient manifold, and plus this expression. So here this tau tilde TPM is in fact the n scalar curvature of n plane section in ambient manifold. So this is a new term what we introduced in 2005, and then this is a general result for any Riemannian submanifold of an n plus m dimensional Riemannian manifold with n and m are at least 2, and we have this Vintigian inequality. This tau nor is bounded above by squared mean curvature plus tau tilde nor TPM minus mo sigma nor. And to my mind, this is a very simple inequality and looking nice. And this can be applied for almost, most of the cases of Riemannian submanifolds of different kinds in different kinds of Riemannian manifolds, like real space forms, complex space forms, Sasakian space forms, quaternionic space forms, etc. Kenmatsu space form, for example. So many of the results is still being appeared in recent years. I can apply this equation, this inequality 5.12 to obtain the results within a couple of lines. And if m is 2, then the case of equality is discussed in terms of the shape operators. If m is greater than 2, then the equality case is again discussed in terms of these shape operators. And here is a simple proof. The simple proof is that in the equation of Gauss, I just put T xyz as R xyzw minus R tilde xyzw. And here R is the Riemann curvature tensor on the Riemannian submanifold. And I take zeta to be second fundamental form of the immersion. Then I see that this equation 5.18 is satisfied immediately, and then I calculate this tau tilde nor TPM, and it comes out to be this expression. We also calculate squared norm of the trace sigma, and it comes out to be n squared norm of the mean curvature vector. And then I use these three equations in the main equation of the Vintigian inequality for Fulcrunity tensor 4.4, and we obtain 5.12. It is so simple. So I'm not going to discuss the applications of this inequality in different cases, but I can show you that there are many. I don't know where to stop, but here are further developments in corresponding areas. So there are some results I can show in these slides. But I think we already have spent 90 minutes. But these are some results, and you can see the results have been written by many geometers across the world in different areas, and it is across the world means they are from the different part of the world, and they are published in different kind of journals as well. One of the main paper was published in Journal of Functional Analysis, and in fact the DDBB conjecture was settled in that journal. Here is some development about Vintigian inequality in pseudo-Riemannian geometry. There are some researches Here I have proved one inequality for scalar curvature for pseudo-Riemannian submanifolds in pseudo-Riemannian manifolds. This paper was published in Journal of Geometry and Physics. Here are some developments, Vinson-like inequalities in Hermitian geometry, one can see. Here are some developments in Sasakian geometry. They also have proved Vinson-like inequality for Riemannian submergence. In fact, now there is a more general term used as Riemannian maps, and it in fact includes both immersion and submersion. I don't know if the Vinson-like inequalities have appeared for the case of Riemannian maps, but I'm sure it can be obtained easily. Here is the idea of Vinson ideal submanifolds, and they proved that they are Mobius invariants. So there is a good interaction with the Mobius geometry. Some results also have appeared for statistical submanifolds. In fact, I have one more general idea of algebraic Gauss equations for statistical submanifolds, and I have further results of Vinson inequality in that case, and I can apply my results, and I easily can obtain these results as a particular cases. But those results are still, they are in my notebooks, and I have to edit them and put them on record. Here are some developments, Vinson type inequalities for submanifolds in product and word product submanifolds. And this is the recent development about normal Ricci curvature inequality. This normal Ricci curvature inequality, it is stronger than the Vinson inequality, and here they have presented some related results like Wacher-Wenzel inequality. So this is just rising conjectures regarding a common generalization. These concepts are coming from linear algebra, and here are the references you can see. Here is the idea of conjecture. How big can the commutator of two matrices be, and how big is it typically? It is also one nice paper which was a motivation point in the settling DDBB conjecture. There are a large number of papers by Bang-Yan Chen, and here is the idea SS Chern, minimal submanifolds in a Riemannian manifold, where he asked the problem. I have tried to put as many good papers as possible in the connection of DDBB conjecture and Vinson inequality appeared so far, and very soon I will put all these results what I have presented in this talk are not published yet, and I have to edit them and to put them for publication at some good place if possible in future. You can see there are 160 references in this talk. Thank you so much for your attention. Please feel free to ask if you have any question.
Thank you, sir, for the beautiful presentation about the Vinson inequality in different aspects. And I think you almost cover all the data about the Vinson inequality. And I feel that the audience will get motivation to do research in this topic also. So any questions from the audience? So I think no questions are there. So thank you so much, sir.
Thank you. Thank you so much.
So thank you, sir. Hello.
Yes, please.
Okay, so sir, I am very much grateful to you that you accepted our invitation and gave a very beautiful talk in this summer school on geometry. And you people are always pillar of geometry, and we always inspire with you people. And I am also thankful to Dr. Poonam that she accepted my request to be chairperson of this session. So thank you, Dr. Poonam, to you also. So with this, we will conclude this session, and we will take a 20-minute break. And next talk will be by Professor Rakesh Kumar, and that will start at 4. So please be connected, or you can rejoin before 4. So thank you again, sir.
You are welcome. Thank you once more for inviting me to give my some thoughts at this workshop. And if anybody has any question, he or she can contact me on email, my email. So please do not hesitate to ask me anything. And most of the, what you have seen, some 160 references, so they all are present with me. Usually I don't put references if I don't read them before. So if you have any kind of assistance or help, please do not hesitate to ask.
Nitish Kumar has raised his hand. Nitish Kumar.
Yes, please.
Nitish Kumar, are you here? He is gone. Nitish Kumar. No. I think he has left. So, okay, sir. So, thank you.
Okay. Thank you so much.
राकेश सर, गुड इवनिंग।
हाँ, गुड इवनिंग सर।
सर कैसे हैं?
जी बढ़िया सर, आप सुनाइए।
बहुत बढ़िया सर।
बहुत अच्छा लगा सर आपको मिलके।
सर मुझे बहुत खुशी हुई कि मैं आपका लेक्चर सेशन शेयर कर रहा हूँ।
जी जी जी। ये तो गौरी शंकर जी ने अच्छा किया, हम सबको मिला दिया इन्होंने।
जी 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 जी।
हाँ जी हाँ जी। और सब बढ़िया सर, घर पर
सर
सब
बढ़िया
ठीक ठाक?
बढ़िया बढ़िया सर। आपका अभी पोस्ट देखा मैंने, उसके
हाँ
बारे
जी।
में भी आपसे डिस्कस किया जाएगा थोड़ी देर बाद।
जी 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 हाँ जी।
जी जी।
हाँ जी। और वहाँ पे ठीक चल रहा है सर आपका?
जी सर बढ़िया, सब कुछ ठीक है अभी।
बढ़िया सर। चलो इनका बड़ा अच्छा हो गया, बहुत दिन की थी ये।
अच्छा
इतनी
अच्छा।
लंबी सक्सेसफुल होना बड़ा लंबा काम ही है सर।
हाँ हाँ सही बात है।
हाँ जी।
नहीं, गौरी सर को काफी एक्सपीरियंस है।
जी 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 हाँ जी। वहां पे भी इन्होंने बहुत कराए हैं जहाँ
जी जी।
वनस्थली में। जी
हाँ
हाँ
जी।
जी। नमस्कार गौरी सर।
गौरी सर नमस्कार।
गौरी सर
हेलो राकेश जी, हाउ आर यू?
नमस्कार कृष्ण सर।
नमस्कार, कैसे हैं?
जी बढ़िया सर, आप सुनाइए।
बहुत अच्छा, बहुत दिन बाद मिल रहा है। सब ठीक है घर में?
हाँ जी जी सर, जी सर, आप सुनाइए कैसे हैं सर आप?
चल रहा है, ठीक है। बाद में फुर्सत में कभी बात करेंगे।
जी जी
हाँ,
जी।
ऐसे तो ठीक है सब कुछ।
हम
हाँ।
तो सोच रहे थे ये फिजिकल होती तो आपके पास आके मिलते सर।
आपने अच्छा बताया, फिजिकल होते तो।
जी जी हाँ जी।
फिजिकल ही है, लेकिन कॉन्फ्रेंस तो ऑनलाइन बन गया है।
जी 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 हाँ जी हाँ जी।
हाँ 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 हाँ। नहीं,
और
जरूर हम लोग मिलेंगे। as soon as this pandemic ends, तो हम
जी
लोग मिलेंगे। ऐसे
डेफिनेटली
भी
सर, डेफिनेटली।
तो पटियाला में सब ठीक है अभी?
जी 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 सब बढ़िया सर, हाँ जी सब ठीक ठाक है।
अच्छा 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 अच्छा।
आप लगाइए चक्कर सर। अब तो हमारे वाइस चांसलर सभी आपकी इंस्टीट्यूट के ही
हाँ,
हैं।
अरविंद है। हाँ हाँ
जी जी
एग्जैक्टली। तो चक्कर तो लगाएंगे, लेकिन अब ये पैंडेमिक थोड़ा खत्म हो जाए। जब
जी
तक
जी
ये खत्म होता ना, तब तक
जी
लाइफ थोड़ा डिफिकल्ट हो गया है।
जी जी। कल
हाँ।
कल बाई चांस ही मेरी वाइस चांसलर साहब से मुलाकात हुई थी,
अच्छा।
तो तब आपका जिक्र हुआ।
ओ आई सी आई सी। हाँ।
तो वो एक्चुअली मेरे से पूछने लगे भी मेरा डिसिप्लिन कौन सा है। तो
अच्छा।
मैंने बोला मैथमेटिक्स। वो कहते चलो
हाँ
मैथमेटिक्स में आगे किस टॉपिक पे काम करते हैं। मैं कहा डिफरेंशियल ज्योमेट्री में।
अच्छा।
तो तब उन्होंने आपका नाम लिया।
आई सी।
तो कह रहे हमारे वहाँ पे कृष्णेंदु जी भी वही ज्योमेट्री में काम करते हैं। मैं कहा हाँ जी वही करते हैं, हाँ जी।
हाँ
तो
हाँ। नहीं नहीं, मैंने उनको बताया था कि मैं गया हूँ, और पटियाला यूनिवर्सिटी में मेरा काफी दोस्त वगैरह है।
जी जी
तो वो हमको बोले थे कि यू कम समटाइम आफ्टर थिंग्स आर ए बिट
बिल्कुल।
स्टेबल।
जी जी जी।
हाँ हाँ।
तो
अभी तो वो कभी कभार व्हाट्सएप में ना, आपके वहाँ पे जो नेचर है, जैसे पंछी हो गया,
जी जी जी
उनके
जी
फोटो रहते हैं। आई थिंक ही गोज
हाँ
मॉर्निंग वॉक और समथिंग, एंड देन ही टेक
जी 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 हाँ जी।
हाँ हाँ हाँ।
तो
नहीं,
गौरी जी स्टार्ट
पटियाला में
करें?
हमको काफी अच्छा लगा था। वो आपने जो कॉन्फ्रेंस किए थे ना, मैं फैमिली लेके गया था, दैट वाज ए काइंड ऑफ
जी
वेरी
जी हाँ जी
नाइस
बिल्कुल बिल्कुल हाँ
एक्सपीरियंस।
जी। जी जी।
हाँ हाँ
सो इस खत्म के बाद करते हैं पर प्लान सर कुछ ना कुछ।
हाँ हाँ हाँ, जरूर जरूर।
जी जी जी
गौरी
सर,
सर
जी
स्टार्ट करें?
सर स्टार्ट किया जाए।
हाँ
हेलो।
सर, 4
हाँ
तो
हाँ,
बज गए।
स्टार्ट करिए। हाँ
Yes. So in this session, the speaker is Dr. Rakesh Kumar from Punjab University, Patiala, and he will talk on study of null hypothesis of Lagrangian manifolds with rigging technique. And for chairing his session, I invite my younger brother, Dr. Sachin, from Central University of Himachal Pradesh. So over to you, Dr. Sachin.
थैंक यू सर, थैंक यू। Good evening to one and all present here. I welcome you all to this session. I am honored that Professor Gauri sir has given me the opportunity to preside over the lecture session of an admirable and young differential geometer, Dr. Rakesh Kumar. He has been a meritorious student from the very beginning. He has achieved gold medal in MSc at Punjab University Patiala in 2002 and qualified CSIR NET with JRF in 2003. Dr. Rakesh was appointed as an assistant professor in the same university in 2005, where he had achieved gold medal. He completed his PhD in 2008 under the supervision of Professor R.K. Nagaich, well-known differential geometer. Dr. Rakesh is interested in differential geometry with indefinite metric, null submanifold, rigging technique, theory of submersion, and statistical manifolds. Dr. Rakesh has supervised 6 PhD students and published more than 65 research papers in journal of national and international repute. If you wish to see the detailed profile of Dr. Rakesh, then you can visit the link posted in the chat box. Last but not least, in my personal opinion, Rakesh sir is very hardworking and good human being. He has always been helping the people of the differential geometry community to the best of his ability. Welcome, Rakesh sir. Over to you.
Thank you, Dr. Sachin, for very nice words for me. I am highly thankful to you. So let me first of all share. Just any one of you, is this page is visible to all of you?
Yes, visible is.
Okay, thank you, Dr. Sachin. Again, thank you very much for nice words for me. I am highly thankful to organizers of this summer school, Professor Gauri Shankar ji and Professor Krishnendu sir, for giving me this opportunity to interact with all of you, to share my knowledge on null hypersurfaces with all of you. The title of the talk is Study of Null Hypersurfaces of Lorentzian Manifold with the Rigging Technique. So I hope before I start, so it is a request to all the participants kindly mute so that I can speak. So I hope most of you have already know about the geometry of hypersurfaces and submanifolds of Riemannian and semi-Riemannian manifolds. But the geometry of null or light-like hypersurfaces and submanifolds of semi-Riemannian manifolds is a recent one, and it was introduced by Bazanco and Dugal almost 15 years back. Now the geometry of null hypersurfaces and null submanifolds of Lorentzian manifold with the rigging technique is more recent, and it is introduced by Goriraj and Olia 4 to 5 years back. This technique removes most of the anomalies appeared in the geometry of null hypersurfaces and is more useful and has significant application in mathematical physics and geometry. Therefore, today we shall take a brief exposition to the geometry of null hypersurfaces with the rigging technique. And if any one of you is interested and wish to work on this in this area, then I hope it is a very good direction to work. So let me start. Let me show me the content of the talk. The content is abstract. Then we will discuss brief introduction. Then we will discuss semi-Euclidean spaces, brief about null hypersurfaces, about rigging technique and rigging on almost Hermitian manifolds, and then null hypersurfaces on generalized Robertson-Walker spacetimes and references. So the abstract is, in the study of null hypersurfaces, the main drawback The main drawback is the existence of degenerate induced metric on the hypersurface. To overcome the anomaly due to the degeneracy of the induced metric, we study null hypersurfaces with the fixed rigging vector field. This rigging technique allows us to construct a Riemannian metric on null hypersurface. This is the major application, that rigging technique is allowing us to construct a Riemannian metric on a null hypersurface. Thus, the extrinsic properties of the null hypersurface are related to the properties of Riemannian manifolds. Later, by taking the advantage of almost complex structure of almost Hermitian manifolds, the notion of rigging technique is extended to null hypersurfaces of indefinite Euler manifolds. Here, the rigging vector field enables us to build associated Hermitian metric on the abelian manifold, and which is restricted to again non-degenerate metric on null hypersurface. Finally, we study null hypersurfaces given as a graph of a function of the fiber of generalized Robertson-Walker spacetime. So these are the briefly content which we will cover in this talk. So brief introduction. We know that the study of non-degenerate hypersurfaces and submanifold of semi-Riemannian manifolds has many similarities with the Riemannian one, with Riemannian hypersurfaces and submanifolds respectively. In case when the induced metric on the submanifold is degenerate, we will discuss about the degeneracy and non-degeneracy in our next section very thoroughly. What the meaning of degeneracy or non-degeneracy of a metric? I hope you must know, but we will repeat. So in the case when the induced metric on the submanifold is degenerate or null or light-like, the study becomes more difficult and strikingly different from the study of non-degenerate submanifolds. The primary difference between the null hypersurfaces and submanifolds to non-degenerate submanifold is that in case of null submanifolds, normal vector bundle intersects with the tangent bundle. This is the major difference here in the geometry of non-degenerate submanifolds and in case of null submanifolds. In the case of non-degenerate submanifolds, tangent bundle and normal bundle, they are complementary and orthogonal to each other. But in case of null submanifolds, tangent bundle and normal bundle, they are intersecting. If M is a null submanifolds of a semi-Riemannian manifolds, then a vector of tangent space to the eminent manifold cannot decompose uniquely as a component of tangent space and its component to normal space, because they are intersecting. We cannot write uniquely into component of tangent and normal space. So what it means? It means we cannot use the standard submanifold theory to define induced objects on null submanifolds. So to deal with this problem, null submanifolds and null hypersurfaces were introduced by Bazanco and Duggal by splitting the tangent bundle of the ambient space into three non-intersecting complementary vector bundles. Three. Because in the case of standard submanifold theory, our tangent bundle of ambient space is split into two orthogonal complementary vector bundles, tangent and normal. But in case of null submanifolds, our tangent bundle of the ambient space is split into three non-intersecting complementary vector bundles which are not orthogonal, one problem, and out of them two are null also. Kupeli also deal with this problem but in different way. Bazanco and Duggal's approach is basically extrinsic, comparatively easy also, in contrast to the intrinsic one developed by Kupeli. Our aim is to discuss extrinsic approach given by Bazanco and Duggal Application point of view, the geometry of light-like hypersurfaces and light-like submanifolds is needed to fill an important missing gap in the general theory of submanifolds. Moreover, the growing importance of light-like hypersurfaces and submanifold in mathematical physics, particularly their extensive uses in relativity, make this topic a present of scenario. So this is the reason we are here to discuss null hypersurfaces and submanifolds. So before going directly to the geometry of null hypersurfaces, let me give you the idea about semi-Euclidean space. Euclidean space we know, or you can say that Riemannian manifolds we know. Now we will discuss semi-Riemannian manifold or semi-Euclidean space. So in very easy way, I hope you must enjoy. So let V be a m-dimensional vector space with symmetric bilinear map G from V cross V to R. This symmetric bilinear map G is said to be degenerate. I told you in my introduction I use the word degenerate and non-degenerate many times. So what is the meaning? When G is said to be degenerate, G is said to be degenerate on a vector space V if there exists a non-zero vector on the vector space such that G of xi V is equal to 0 for every vector belongs to vector space V. It means if there is existing, now listen very carefully, if there is existing a non-zero vector which is orthogonal to each and every vector of vector space. If xi is orthogonal to each and every vector of vector space, then it must be orthogonal to itself also, because xi is also element of V. It means G of xi is equal to 0. By taking inner product, we have a norm, then by norm becomes 0. Norm of xi becomes 0. Length of xi becomes 0. So what it means? It means if there is existing a non-zero vector whose length is 0, norm is 0, then that type of G is called degenerate. Otherwise, it is called non-degenerate. In other words, G is said to be non-degenerate if this happens, if G of U V is equal to 0, if U is orthogonal to V for any vector V, for non-degeneracy, this U should be 0. It should not be non-zero. It is important, now it is very important line here. It is important to note here that non-degenerate. So we have two types of matrices by symmetric bilinear form: degenerate, non-degenerate. Degenerate means we have a non-zero vector whose length might be 0. Non-degenerate when we have no such vectors. Clear? So if you have non-degenerate symmetric bilinear form on the vector space V, it may induce either non-degenerate or degenerate symmetric bilinear form on the subspace of vector space V. Now radical, what is the meaning of radical? The radical or null space of vector space V is denoted by radical V.